Hello, in this video I'll be talking about section 12.5, which extends what we've been talking about in terms of similarities specifically to right triangles. And this first theorem actually came up in a homework problem, so we should be able to understand this fairly easily. In any right triangle, the altitude to the hypotenuse, so let's draw a right triangle, pardon me. I can make that look a little bit better. So here's my right triangle, and I'm going to draw in the altitude to the hypotenuse. Remember, altitudes are perpendicular. So this altitude has separated the original triangle into two smaller triangles, and what we can see is that they are similar to the original triangle and to each other. And here's the gist of that. I'll specifically label a couple of angles here. So if I look at triangle ABC, the original one, triangle ABC has a right angle, a blue angle, and a green angle. Let's look at this triangle here. Triangle ADB has a right angle and a blue angle. So by angle, it is similar to the big triangle. Now we have to get the order right. In the big triangle, A is where the right angle is. B is where the blue angle is, and C is where the green angle is. In this smaller triangle at the bottom, the right angle is at D, and the blue angle is at B. By process of elimination, the last one is A. We can actually show that angle DAB is congruent to angle C. Similarly, triangle ABC is similar to this triangle on the top. The triangle on the top has a right angle at D. It has a green angle at C, so that goes last. By process of elimination, there's an A here. We could show that angle CAD is congruent to angle B. So these are similar, but they're similar in a way where things are kind of backwards and twisted. It's hard to intuitively understand this. What I recommend is to think in terms of each right triangle in this picture has a hypotenuse, a long leg, and a short leg. If you think in terms of left and right and top and bottom, because of all the twists, it's going to be hard to match these up. But if you think hypotenuse always matches hypotenuse, short leg always matches short leg, and long leg always matches long leg, it'll be a little more consistent. And I'll demonstrate that in a couple of problems at the end of this section. So with these similarities in mind, there are some rules that explain how the various lengths here, right? 1, 2, 3, 4, 5, 6, if we count the whole hypotenuse. There are 6 different things we could measure in terms of lengths here, and they're related in different ways by the proportionality. So I'll show you what the book says, but I'm going to encourage you to not worry about learning this theorem word for word. That this theorem comes from the proportionality. If you understand the similarities, there's really no need to memorize what these say. I would recommend against it, because if you try to memorize these and get one thing swapped in your head, it's going to be wrong. If you remember, oh, when I have a picture like this, all 3 triangles are similar, then that'll lead you to all the right conclusions. So these theorems, these theorems will use this phrase called geometric mean. If I have 2 numbers, the geometric mean is when I multiply those numbers together and then take the square root. So for example, the geometric mean of the numbers 4 and 9 would be the square root of 4 times 9, which is the square root of 36, which is 6. It's sort of like saying what number comes in the middle between 4 and 9 from a ratio point of view. Because what you might notice is the ratio of 6 to 4 is the same as the ratio of 9 to 6. So from the point of view of ratios, 6 is actually right in the middle between 4 and 9, even though from the point of view of counting, it's closer to 4 than to 9. So this paragraph just repeats this idea. Don't worry about memorizing, but I will show you how these results work. So given a right triangle and an altitude to the hypotenuse, so let's draw a picture. So number 1 says the altitude is the geometric mean of the segments into which it separates the hypotenuse. So let's call this x, and let's call these a and b. Here is my whole hypotenuse, but by drawing in this altitude, I've separated it. And this is telling us how x and a and b are all related. Let's think about similarity. And I'm going to set up ratios by thinking about short leg, long leg, and hypotenuse. So if I look at this triangle here, I will notice that I have labeled the long leg and the short leg. So I'm going to think about the ratio of long leg to short leg. In this triangle, the ratio of long leg to short leg is a over x. In the smaller triangle at the bottom, the long leg is x and the short leg is b. So the ratio of long leg to short leg is x over b. But what we just learned is that in this kind of picture, a right triangle divided into two right triangles, all the triangles are similar. So those ratios are the same. The corresponding sides are in proportion. Ratio of long leg to short leg is the same. If I cross multiply here, I get x squared equals a times b. So x is the square root of a times b. That's a geometric mean. I don't think there's any need to memorize this. I would just set up this ratio whenever you need it. That's number 1. Number 2 says each leg is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So let's try to make sense of that. Let's call this y. So y is the leg that I'm going to find. And let's say c is my length for the whole hypotenuse. So again, I'm going to set up a ratio. If I look at this triangle here, I will notice that I have labeled the long leg and the hypotenuse. So I'll set up the ratio of long leg to hypotenuse. In this upper triangle, the ratio of long leg to hypotenuse is a to y. But now let's look at the big triangle. In the big triangle, the long leg is y and the hypotenuse is c. So the ratio of long leg to hypotenuse is y over c. All the triangles in this diagram are similar, so those ratios are equal. If I cross multiply, I get y squared equals a times c. So y is the square root of a times c. It's the geometric mean of the entire hypotenuse c and the part of the hypotenuse that's up here across from y. But again, don't worry about memorizing these. Look for what numbers you have, what numbers you're trying to figure out, and just start setting up ratios like long leg to short leg to hypotenuse, hypotenuse to long leg. Whatever seems relevant for that problem, set that up and solve the proportion. So let's actually do some problems here. So in this example, suppose I want to find x. So we might want to look at, well, what do we have here? Which triangles do we have various things labeled? So for the big triangle, I notice that I know the hypotenuse. I know the long leg, I don't know the short leg. For the triangle at the bottom, all I have is the short leg. For the top triangle, I have the long leg and the hypotenuse. So it seems like what we have most often is long leg and hypotenuse. Let's try a ratio of long leg to hypotenuse. In the big triangle, the long leg is 10, and the hypotenuse is 8 plus x if I go all the way across. In the triangle on the top, the long leg is 8, and the hypotenuse is 10. You have to change your perspective. I'm only looking at this triangle at the top. For this triangle at the top, 10 is a hypotenuse. The 10 is a hypotenuse from one point of view and a long leg from another point of view. The triangles are similar, so those ratios are equal. If I cross multiply, I have 8 times the quantity. 8 plus x is 10 times 10. 64 plus 8x equals 100. 8x equals 36. X equals 36 over 8, which is 9 halves, or 4 and a half. Pardon me. Let's look at this one over here. I want to find y and z. Look at the various triangles and think about what's labeled. In the big triangle, short leg, long leg are labeled. I don't really know the hypotenuse because I only have part of it. For this triangle down here, all 3 are labeled. For this triangle here, short leg and hypotenuse. Actually, sorry, I goofed here. This problem is harder than it needs to be. My apologies. Let's change it so that these are a little bit easier. Let's make the 6 and the 8 like this, and this is z. Sorry about that. It was doable the way we had it, but it's a much harder problem. So again, let's look at the different triangles and try to see what's what. In the big triangle, I know the short leg and the hypotenuse. In the triangle up here, I know the short leg and the long leg. In the triangle here, I know the short leg and the long leg. So it looks like short leg and long leg is a good ratio to use. In this triangle, the short leg is y and the long leg is 8. In this triangle, the short leg is 6 and the long leg is y. If I cross multiply, I get y squared equals 48. So y is the square root of 48, which simplifies to 4 root 3. Now, how can I find z? That's actually pretty easy now, because I can just use Pythagorean theorem. By the Pythagorean theorem, just in this triangle on the bottom, leg squared plus leg squared equals hypotenuse squared. So y squared plus 6 squared equals z squared. Y squared we already know is 48 plus 36 equals z squared. So we have 84 equals z squared. Z is the square root of 84, which is 2 root 21. I don't know why I wrote 11. Okay, so in this section, most of your practice will be just applying these to compute things. Don't memorize the theorems besides the fact that you have similar triangles. In each case, it's really recommended to just slow down and think, what triangles do I have? What sides do I have? And begin every problem by just setting up a ratio like this. Okay, that is it for this video.